Good day from Chem Help ASAP. Let's discuss some general ideas of infrared spectroscopy and how it applies to organic molecules. IR is a spectrophotometric technique that relies on infrared photons. The useful range of wavelengths for organic molecules falls in the range of 0.25 micrometers to 1 micrometer. IR photons have an energy that can induce vibrations in organic molecules. So IR spectroscopy is often said to be a form of vibrational spectroscopy. So here is a simple molecule, methanol. When the correct wavelength of IR light hits this molecule, the molecule absorbs the photon, and the CO bond in methanol begins to vibrate. We often think of bonds as springs. Under that model, the photon causes the CO to begin to vibrate like a spring, stretch, and compress. The absorption of the IR photon involves a specific frequency or wavelength that matches the energy of the bond. That absorption of IR photons can be detected and measured and interpreted as evidence that the analyte molecule, methanol, contains a CO bond. Let's see a sample spectrum. Here is the IR spectrum for methanol. This spectrum was pulled from the spectral database of organic compounds. A link to the full database is in the bottom right. Okay, let's get our bearings on this spectrum. The x-axis is in wave numbers. Wave numbers are inverse centimeters. So this is the inverse of the wavelength of the photon in centimeters. Wave numbers are kind of a weird dimension to use, but they've been used essentially forever in IR spectroscopy, and they're not going away anytime soon. So the x-axis runs from 400 on the right to 4,000 wave numbers on the left. In practice, we will mostly only interpret peaks from about 1,000 wave numbers and higher. The y-axis is percent transmission. This is interesting. For many energies or wavelengths, the molecule does not absorb the photons. Zero absorption corresponds to 100% transmission. The photon simply travels right through the sample. It's when the signal line dips, transmission drops, that the molecule is absorbing the IR photons and undergoing bond vibrations. Therefore, the signals in an IR spectrum correspond to the dips, which are called absorbances, although I will call them peaks sometimes. Just remember that in IR, the peaks are down, not up. The absorbances are referenced based on the x-axis position of the bottom of the dip, the bottom of the absorbance. We have a number of absorbances in this spectrum. The deeper dips are said to be strong absorbances. The shallower dips are said to be moderate or even weak absorbances. Not all absorbances can be interpreted and assigned to a functional group. The strong absorbances in this spectrum can be assigned. The strong absorbance at 1,030 wave numbers corresponds to the stretching of the CO bond in methanol. This broad and strong signal on the right is at about 3,340 wave numbers and corresponds to the stretching of the OH bond. Now, we already know what this molecule is. It's methanol. But these signals, a CO stretch and OH stretch, are consistent with the identity of the molecule. Based on the data, we know that the molecule must contain an alcohol. And of course, methanol does contain an alcohol. IR spectroscopy is very good at identifying many functional groups, but it is less useful at identifying a specific molecule. For example, the IR spectrum for other alcohols like ethanol, propanol, or butanol would look much like this spectrum. So IR is best for identifying functional groups. That is a very quick introduction to IR spectroscopy and reading an IR spectrum. If this video was helpful, please click the like button, subscribe to the channel, or make a comment. Take care.